All right, we're going to go ahead and get started. Thank you everyone for joining us. Today we're going to hear from Joel Fajans. He is a professor at UC Berkeley. He got his PhD from MIT and then fairly quickly after joined the Berkeley faculty and has been there ever since. He's won a number of awards from the Hertz Foundation and the American Physical Society, and he's a fellow of the American Physical Society. His research is in non-neutral plasmas and specializes in antihydrogen, which we'll hear about today. Joel has also taught the basic electronics lab at Berkeley for a long time. In fact, 20 years ago, I took this class at Berkeley. And in fact, it was one of my favorite memories of my undergraduate. In particular, we did a project at the end in which I built a little trigger board, and that is what I teach today. So there's a lot of continuity from what I learned in Joel's class to what I'm doing today. So thank you, Joel, for joining us. Let's hear about it.
Thank you, Lauren. And okay, let's get this to go on. Yes, it's on. I should also say that Lauren was one of my best ever students in this class, so there's a lot of mutual admiration, and at least in my direction towards Lauren, well-deserved. In any case, I'm going to be talking about measuring the effects of gravity on antimatter. This is a project that I've done with the help of the Alpha collaboration, which is a CERN collaboration. My own personal research on this project actually is funded by plasma physics and fusion physics, which is a curious connection. But in any case, what we're going to be discussing today is whether or not antimatter should be affected by gravity. And ever since antimatter was proposed by Dirac, and people have speculated about how it would fall towards in the fields of gravity. In fact, some people have speculated that antimatter might fall upwards. Now, admittedly, that's probably mostly beer hall conversation, but it's still been a speculation that's been out there for a very long time. And I'm here to tell you today that antimatter, unfortunately, does not fall upwards. It falls downwards, as everybody expected it would fall. And that means I don't have a really wonderful physics results to talk to you about today, but what I'd like to do is explain why this has remained a question that people have been interested in for now about 100 years or so. I'll talk about some theory experiments, why the idea of some sort of weird gravity just doesn't simply go away, and talk about some indirect experiments, including one, the very first one, which was done here at Stanford, actually. And then I'm going to discuss, that's the first and failed direct experiment, to tell you the truth. But then I'm going to explain to you how we measured gravity and also discuss some of the technological hurdles that we had to overcome to make this a successful measurement. So what are we talking about? Everybody knows apples fall towards Earth, and everybody believes anti-apples would fall towards an anti-Earth. So the question we want to know is, how does an anti-apple fall in Earth's gravitational field? Now, Einstein's weak equivalence principle, of course, insists that antimatter will fall in exactly the same fashion as normal matter. And the weak equivalence principle has been satisfied in every single test that it's been tested with so far. There are also, in addition to the weak equivalence principle, there are special arguments about antimatter and gravity, all of which insist that it shouldn't have any weird properties. Here's a list which I simply stole off of Wikipedia. I'm not going to have time to go into the details of any of these arguments, but I will say that all of these arguments have been challenged. They rely on various assumptions, and all of these challenges are listed in a rather long paper written some years ago by Nito and Goldman. So why should we even, given all of this, why should we even consider whether or not antimatter could possibly do anything other than fall downwards? And the reason why we should consider this is that physicists have been wrong about these sorts of questions before. For instance, Wolfgang Pauli said that the Lord is not a weak left-hander, and I'm ready to bet a very high sum that experiments, these would be parity experiments, come out with symmetric results. I do not know if Pauli actually made that bet that parity would be conserved, but I do know that Richard Feynman bet $50 that it would be conserved, which was a substantial sum at the time that he made the bet. Now, of course, all right, it wasn't conserved, so people fixed that up. In particular, Levlando added charge to this. And so we had CP conservation. And of CP conservation, according to oral history, he said, if it's violated, I will hang myself. He didn't, which is a fortunate thing. But in any case, nowadays, more modern people, we have the dilemma that we've lost 95% of the universe in the last 40 years. This is getting to be embarrassing, folks. Really embarrassing, and needs to come to an end. Something needs to be done. We need to find all of that matter. And also things like the cosmological constant. Einstein called it his worst blunder, I believe. But it turns out to be necessary to understand things. So if all of these people can get these sorts of things wrong, and they were certainly brilliant physicists, maybe we shouldn't be so arrogant to assume that we understand everything, and there aren't some oddball things that could happen. And weird gravity falls into this category. So what in particular drives searches for weird antimatter gravity? The fact that we already know that something is wrong with our understanding of gravity. And that comes from the fact that the current theories of the Big Bang predict that almost equal amounts of matter and antimatter should have been produced in the Big Bang, and possibly all annihilated away to nothing, but we should be able to see large amounts of antimatter in the universe. And that simply is not true. Little antimatter has been detected by various satellites that have gone looking for antimatter. And in addition to that, if there were, for instance, antimatter galaxies out there, there would be fronts between the antimatter galaxy and the galaxies. And on those fronts, you would get positron annihilation at 511 keV, which would be a fairly detectable signal. And we don't see any of that. So there just doesn't appear to be very much antimatter in the universe. And this is called the baryogenesis problem, and it does not have a solution. There are some CP violating weak interactions that do violate baryon number, but their known weak interaction processes that do this are not nearly strong enough. Now, if you were to violate the weak equivalence principle somehow or other, that would easily solve the baryogenesis problem. And multiple theorists have made predictions about how this might come about. Once again, these are from Wikipedia. I'm not going to go into any detail. But these are reasonable theorists. They have jobs at prestigious or universities in Europe. These are not crackpots. And of course, I get a letter every 3 or 4 weeks from people explaining to me how this all is supposed to happen. But these are not in that category. They're reasonable theories. So, have there been experimental evidence against antimatter gravity? There have been a lot of indirect measurements that suggest that gravity just isn't weird in any particular way. And here's a list of some of those experiments. Again, I don't have time. But all of these experiments have been challenged for one reason or another. For instance, in a paper in 2016, the author wrote, however, for antimatter, all of them exploit some additional assumptions, such as gravitational properties of virtual particles, the physical significance of the absolute values of gravitational potentials, CPT invariance, and so on. And also, all of these experiments have been critiqued in this paper by Nito and Goldman that I mentioned earlier. So, none of these experiments have been what I might call a direct experiment. They've all been indirect experiments, which rely on relatively subtle physical properties to make their measurements. What you really want to have here, or at least I really wanted to have here, is a direct experiment, a Galilean, dropping the ball off of the Leaning Tower of Pisa type of experiment. Now, yes, I do know that that experiment is apocryphal. But in any case, that's a sort of direct measurement that we would like to make to answer this question with some finality. And the very first attempts to make this was actually done here at Stanford by Fairbanks. Perhaps some of you have seen knew him perhaps. I don't really know, but Fairbanks was a great experimentalist. And what they did was to try and measure gravity with electrons, by dropping electrons. They planned to follow up with positrons. The positron sources at the time were insufficient for them to do the follow-up experiment. But the experiment is nonetheless famous because it came up with quite a puzzling result. The result that they found is that gravity seems to have absolutely no effect on electrons, which are being dropped. And this actually wasn't quite as confusing as they might have been, because by that point, there was a theoretical explanation for why this would be. And to explain that reason, let's talk about what Fairbanks was essentially trying to do, which was to drop an electron inside a metal tube which was there for shielding. And the theory reason, by Schiff and Barnhill, they pointed out that the tube itself is going to have electrons in it, which are going to behave like an electron gas. And that gas is going to fall under the influence of gravity. How far will it fall? Well, it will fall to the level at which it makes an electric field which points upwards, which exactly cancels gravity. Now, one of the things you learned in freshman physics is that if you have a boundary condition, uniform electric field on that boundary condition, that boundary will exist inside the tube as well as outside. So there's going to be an electric field which is going to push up on the electron just as hard as the field gravity is pushing down. So you might expect that it would not fall. Well, if that's the case, obviously what to do is you can measure a potential difference. There should be a voltage between the top and bottom of this tube, and you should be able to measure that. So you put a multimeter on the top and one lead on the top, one leader on the bottom. And then you realize that the electrons inside the leads themselves are going to sag. And the expected measurement would be precisely zero potential drop between the top and the bottom. All right, it sounds like an explanation, except that it gets more complicated, because a later group of people pointed out that the ions in the crystal lattice inside the tube are going to sag as well under the influence of gravity, and perhaps since they're heavier, they're going to sag more than the electrons, which would cause there to be an electric field which is pointing downward, so the electron should have actually fallen at a rate which is faster than the rate predicted by gravity. Now, these two pictures can actually be reconciled by considering temperature effects, but the whole situation is really quite complicated and is unresolved to this day, exactly what happened in Fairbanks' experiment. But the real mystery about Fairbanks' experiment is that it shouldn't have worked at all. One of the reasons why it shouldn't have worked at all is because of a phenomenon called patch fields. One of the things you learned in freshman physics is that if you take a metal container, it's a Faraday cage, right? And there are no electric fields inside of a Faraday cage. This, like many things that you learned in freshman physics, is a complete lie. There are, in fact, very strong electric fields inside a closed metal container, which come from patch fields. Patch fields are things that are fields that are developed from grain boundaries, oxide layers. There are several mechanisms, but they all cause there to be fields inside of a metallic tube. In our apparatus on the alpha experiment at CERN, our tube is roughly similar to the Fairbanks experiment, and we measure fields of about 10 millivolts per centimeter. That is an enormous field. And if you think about what it would do if you're trying to measure gravity, you can calculate the electrical forces on a positron and the gravitational forces on the positron, and you discover that the electrical forces are about 10 orders of magnitude stronger than the gravitational forces. So it appears absolutely hopeless to try and measure gravity with an electron inside of one of these tubes. And that appears to be the case. And so in the Fairbank experiment, you wouldn't have expected them to fall downwards. You might have expected them to go downwards very fast, accelerate upwards very fast. They might have gone sideways, but whatever they would have done, they shouldn't have just stayed there, sitting in one place. In any case, because of this, all research subsequent to this on gravity and antimatter has been conducted or intended to be conducted with neutral matter, things like antihydrogen atoms, which has been proven by us to be charge neutral to about 1 part per billion, which is good enough to do the experiments at the level that we would like to do that. You could also perhaps use positronium. So just to remind you, what is antihydrogen? Well, this is actually an electron atom in an elementary school model. Substitute an antiproton in the center, which is negatively charged. Substitute a positron, positively charged particle on the outside, and if you have antimatter. And there are 3 experiments at CERN which are intending, or in our case, have measured gravity using antihydrogen atoms. Each of these experiments has about 60 people, 50 to 60 people working on them. So they're big experiments, a total of almost a community of 200 people or so. There's the alpha experiment, where we've used a magnetic balance to measure gravity. There's the G-bar experiment, which intends to trap antihydrogen plus ions. In other words, take an antihydrogen atom and have 2 positrons rather than simply 1 positron. Why would you do that? It's much easier to manipulate ions than it is to manipulate neutral antihydrogen or hydrogen for that matter. So they can cool them. Their plan is to cool them and strip the ions and make a fountain. And then there's also the AGIS experiment, which intends to make a deflection measurement with an incredibly position-sensitive detector where they send antihydrogen atoms out sideways. Both of these experiments are still probably, you could say, in their beginning stages. So exactly why is the gravity measurement hard? Well, I've already explained the charge problem, but once you've gotten over that by using neutral atoms, you have a problem of velocities. The anti-atoms that we can make have an energy of less than about half a Kelvin. So let's say on the average they have an energy of about 30.3 Kelvin. And that means that they're moving at about 70 meters per second. Now, what would happen if you took a particle and threw it straight upwards at 70 meters per second? Obviously, it would get to the top like a fountain and turn around and come back down. And in fact, it would get to about 250 meters high, which amusingly is about twice the height of the fountain in Lake Geneva, right next to CERN, where all of these experiments are taking place. In any case, unfortunately, I failed to find a funding agency willing to make a 250-meter long ultra-high vacuum chamber, so we have to do something cleverer than that. And for the remainder of this talk, I'm going to explain exactly how we do the experiment, given how fast these particles are moving. But I'm going to begin by talking about where we get the actual particles. We get our positrons, which were first, of course, discovered by Carl Anderson in cosmic rays in the 30s. We get them from a radioactive source, a sodium-22 source. It's an artificial element. It is quite radioactive. And it puts out positrons at about 100 keV, which is much too energetic for us. So the very first thing we do to these positrons is we send them into some solid neon, frozen neon gas, which acts like a moderator. So the positrons come in at 100 keV, and they come in, many of them annihilate, but they basically rattle around and they thermalize down to an energy of about 1 eV. So what's going to happen next? Well, remember work functions. A work function is, and the solid state people, please don't give me a hard time here, it's like an electric field which points inwards for electrons, pushing the electrons back into the metal so they don't pop out. But positrons have the opposite sign. So positrons will be popped out of the surface of the solid neon by the work function itself, and they'll pop out with the value of the work function, which is about 1 eV. So that gives us a copious source of 1 eV, atoms. And the next thing we do is to use a drift tube to transport them into something called a circopositron accumulator. This is a device that uses elastic and inelastic collisions to cool them down further and turn them into a plasma. It's a complicated device. It's revolutionized positron physics, but unfortunately I really don't have time to go into the details of how it actually works. The net result is that every few minutes we can get about 10 million positrons, and we can transport them into a trap which is called the Penning-Momberg trap. So what is the Penning-Momberg trap? Penning-Momberg traps are used to confine charged particles and also plasmas, because these actually turn out to be plasmas. And the way it works is that longitudinal confinement is provided by imposing voltages on a set of electrically isolated cylinders. So you can make potential wells in the longitudinal direction. And you can even make the wells pointing in opposite directions, so you can park some antiprotons right next to some positrons, if you choose to do this. But the positrons in particular, but even the antiprotons, have very strong radial electric fields because there's 10 million particles in them or something like that, and obviously there are radially outwards pointing electric fields, which you would think would force the particles radially outwards into the walls. This is prevented by using a strong magnetic field which points along the trap axis. Now, what actually happens in more detail, and this will become a little bit relevant later, is that once you have the strong electric field from the positrons, plasmas, and the magnetic field, what happens is the plasmas undergo a motion called an E+B motion, and they end up spinning on the axis. They're quite stable inside one of these traps, and if the plasma is cold, it actually will spin like a rigid rotor. So these traps work incredibly well. To give you an example, the world's main fusion experiment is something called ITER, and it's estimated to cost about $20 billion. Probably it's going to wind up more. The venture capital has invested about $6 billion in fusion in the last couple of years. And the longest confinement times that have ever been achieved in devices like these fusion devices is about 30 seconds. While in our trap, which costs about 10,000 times less, we can confine plasmas for days, if not actually forever. Now, there's a catch, of course, which is that our densities and our temperatures are lower than those inside of a fusion device. But in any case, there are many things that we can do in these traps which can't so readily be done in a fusion device. And I'm going to spend a few minutes talking about some of these plasma effects that we can do inside of a Penning-Momberg trap. So one of them is how to cool the plasmas. Cooling will turn out to be very, very necessary and for us to make antihydrogen. And the good thing is it happens for us without even trying. Remember, there's a strong axial field inside these traps. So the electrons or the positrons are going around in tight little circles, or cyclotron orbiting, and they're just going to radiate their energy away. And that's pretty fast. The time constant is 1 Tesla is about 4 seconds for them to E-fold their radiation. At 3 Tesla, which we also use a lot, it's about half a second. So the energy goes away quite quickly, and you would expect that the energy would asymptote to the wall temperature of the surrounding trap. But here's a problem, because it is universally observed in these traps that they don't get down to the wall temperature. They get hung up at about a temperature of about 100 Kelvin for reasons which are not entirely understood. So we need to get our plasmas down to about 10 Kelvin for all of this to work. So we need to do some additional cooling. And the cooling that we can readily use is evaporative cooling. In other words, if we put our plasma, our positrons, into a well and simply lower one of the sides of the well, the hottest positrons are going to escape. Like in any evaporative process, that leaves the colder particles behind, and the plasma is going to cool. So we can get down to about 10 Kelvin this way, especially if we combine it with adiabatic expansion cooling. And it works very well. The only trouble is it's a temporary effect. So while we can get down to 10 Kelvin, it only lasts about a second down there until it warms back up to to the 100 Kelvin that I was referring to earlier. So we have to turn these positrons into antihydrogen in about 1 second, but that actually turns out to be a feasible thing for us to do. Another thing we can do is to control the density of our plasma. Remember, the plasma is spinning due to this E cross B motion, and it's spinning at a specific frequency. Some of our trap walls has azimuthal segments on it on which we can apply potentials which are oscillating, and that will make an electric field which is also spinning. Under certain circumstances, the spinning rate of this electric field can lock to the spinning rate of the plasma itself. And when that happens, we can control the density, because the density is linearly related to the spinning frequency, the drive frequency over here. So there are only constants involved here. So we can get any density that we want very, very accurately. This is something that they can only dream of doing in a fusion device. In any case, another thing that we can do is to calculate the potential on the axis of the plasma. So here's our plasma. Here's the wall, the grounded wall surrounding the plasma, and we can calculate the potential right on the axis of the plasma. And it's given by a freshman physics formula, but that formula is pretty simple. The central potential is proportional to the density and the radius of the plasma, and perhaps weakly proportional to the wall radius, but that's a constant. So if we can control the central potential and control the density, that controls the radius of the plasma. There's nothing else that's free in this equation. So I've already actually told you how we can do that. We can control the density by this rotating wall, and if you think about the evaporative process, the particles that are going to evaporate are the ones that are on axis, that match the potential of the plasma itself and the wall around it, so we can control the central potential. And then we've controlled all of the parameters here, so our plasmas have to be absolutely identical. And this works incredibly well. It's not easy to develop. It took my graduate student Celeste Carruth a summer, basically, of night shifts, because nobody else believed this was going to work. So all she got was 11 p.m. to 7 in the morning, and it took her a summer to get this to work. But once it works beautifully. You can see here some data of the total number of particles before we applied this technique that Celeste developed, and you can see there's about a 30% variation. And after she developed the technique, the variation went down to about 1% or so, which was very, very good for us optimizing the process of making and particularly trapping the antihydrogen atoms that we want to work with. So where do we get our antiprotons? Well, it turns out that, well, CERN, as you know, its main job is to run the LHC, but the LHC only needs to be charged with particles about every 10 hours. So you might think save on personnel costs, save on energy, and don't run the rest of the CERN complex, which accelerates particles up to the energy that's necessary to inject into the LHC. Just turn it off and only run it once every 10 hours. That doesn't work at all, because the accelerator complex will drift during that period of time. So in fact, that whole accelerator complex at CERN is running all the time, making pulses approximately every 100 seconds of protons. And there are a number of experiments at CERN that work parasitically off of these pulses, which are always being generated. We use some of those pulses. We only need to use a small part of the accelerator complex, this part that's over here. It starts with a LINEC, well, it starts with the source and then a LINEC, and then protons are delivered to the antiproton decelerator. I'm not going to comment on it any further, except one thing, which is to say one part of it, the proton synchrotron, has been in operation only 1 year less than I personally have been in operation. I mean, it's an astonishing thing that this accelerator is still running from 1955 59, I believe it is. In any case, the antiprotons are, the protons are delivered to us through an underground tunnel. They come into what's now pretentiously called the antimatter factory. And there they're slammed into an iridium target where the particle physicists, please don't criticize, again, they rattle around inside the iridium. And they make secondary particles, including antiprotons. These antiprotons are made actually in more or less the same process that the antiproton was made in its discovery by Chamberlain and Segre at Berkeley in the 1950s. But they're made at about 3 GeV, which is too hot for us to use. Fortunately, CERN slows them down. They have a special accelerator. Actually, it's an accelerator running backwards, so it's a decelerator, which slows the antiprotons down to an energy of about 5.3 MeV. And then recently, they've constructed a new electrostatic ring over here, which slows them down further to about 100 keV. And then they go along a beamline into our apparatus, which is this experiment over here. Now, 100 keV is still well too hot for us to be able to functionally use them. So what we do is we send the particles into a degrading foil. A lot of them, which is just a very thin foil, a lot of the antiprotons annihilate inside of that foil. Others wind up at energies that we can't trap, but we get a significant number of antiprotons with an energy of less than about 5 keV, which we can trap in a Penning-Momberg type trap with what you might call a barn door arrangement. You have a trap which has 2 walls. You lower one of the doors. The antiprotons come in. They bounce from the far wall. But by the time they get back into their entrance wall, you've erected that entrance wall and they're going to be trapped inside, where they can be cooled by collisions with electrons. In any case, the net result is that we can get about 50,000 antiprotons every 100 seconds, which is sufficient for our uses. So how do you actually make antihydrogen? Well, the first part of the process is to turn the antiprotons and the positrons into appropriate plasmas, which have the right properties to make antihydrogen atoms that can be trapped. What we need are plasmas which actually closely resemble a sewing needle, the same dimension, the same form, function, and the same shape, basically, as a sewing needle. But in particular, what we need is for the positrons to be very cold, about 10 Kelvin, something I was mentioning before. This turns out to be very hard. And in fact, since alpha started, well, operating in about 2005 or so, I would estimate that about 50% of our experimental time has been spent developing the techniques to make the plasmas that we need to make. The antiproton plasmas also have to be cold, but not quite as cold. And then we can make antihydrogen by simply mixing the antiprotons and the positrons together inside one of these Penning-Momberg traps, where the antihydrogen will be formed due to 3-body recombination. If the antiproton comes close enough to 2 positrons, one of the positrons can be grabbed by the antiproton, creating a very high Rydberg state atom. The other one will be spit off. The other positrons is spit off to conserve momentum and energy. And then the antiproton will, the antihydrogen atom will eventually cool down. We mix them together by just electrostatically tipping the antihydrogen atoms, the antiprotons into the positrons. The 3-body recombination takes over. We make antihydrogen, but the antihydrogen is charge neutral. So it's not going to be confined by the fields that we use to confine the positrons and the antiprotons. We need additional fields to do that. And what we use is to take advantage of the fact that antihydrogen has a small magnetic moment, and it can be trapped in a magnetic minimum, in a Yaffe-Pritchard trap, if it has the right spin direction. And we make an axial minimum by using mirror coils, and we make mirror coils like these coils at the end. This is spinning only to make it visualization purposes. And then we use an optical magnet this one that's snaking back and forth to create a radial minimum. So what we wind up with is basically something in which the magnetic field looks like a bathtub. At the bottom, the center of the trap, there are walls in every direction. Magnetic walls in every direction. The magnetic field increases in every direction. And if the antihydrogen atom is properly spin aligned, and half of them will be at their moment of creation, then the magnetic gradient force that we get from the antihydrogen atom trying to climb these walls is going to repel the antihydrogen back into the center. And this trapping mechanism, so long as it gets trapped in the first place, is very, very good. There's basically no escape from this trap. The only trouble is that even though our octopole magnet is a state-of-the-art magnet, it was fabricated at the Brookhaven National Laboratory, it only has a field of about 1.5 Tesla, which isn't very strong, because that makes that the magnetic moment of the antihydrogen being weak, this means that the trap depth is only about 0.5 Kelvin, which to you atomic physicists may sound like a decent amount. But in fact, it's not very large. And the reason why it's not very large is that we have these positron plasmas which have a lot of charge in them. And that charge makes a strong electric field. There's a potential drop across the plasma. So the natural energy scale is about 1 electron volt. We have to make the antihydrogen in some fashion so it doesn't pick up any of that 1 electric volt in the process of recombining. That's really tough too, and that's the other part of the plasma physics that has gone into making this experiment work. But we need to start with something with this natural energy scale of about 1 electron volt and mix it together with about 40 microelectron volts of energy, otherwise it won't be trapped. And we've worked very, very hard. Lots of people have worked on this problem. And it turns out to mostly depend on the positron temperature. So here's some very, very early data where we had a positron temperature of about 70 Kelvin, and we're trapping only 1 antihydrogen atom in every 30 attempts to trap, each attempt taking 15 minutes or so. This is almost impossible to optimize. But fortunately, we were able to lower the temperature down to about 40 Kelvin, and at 40 Kelvin, we were able to trap an antihydrogen atom about every trapping attempt. And here are some theoretical predictions about what we might have gotten. This is one case where actually nature was kinder to us than the predictions would have said. It turns out that if you can get down to 10 or 4 Kelvin or something like that, you can actually trap as many as 40 antihydrogen atoms in every attempt to trap some atoms. And the attempts only last 5 minutes rather than 15 minutes now. Moreover, we can make some antihydrogen, we can trap it, and then we can bring some more new antiprotons and positrons into our experiment, make some more antihydrogen, and stack on top of the previous antihydrogen that was there. So we've had over 1,000 antihydrogen atoms in our trap simultaneously at that point, though we didn't use that many for our gravity experiment. So the alpha, to go to some technical details, the alpha magnet system is really very, very complicated. Here's a picture of it being wired up. And I'm happy to say that in this generation, I only had to wire about 10 of those wires. There are about 1,000 wires which have to be wired between the magnet leads themselves and the sensor wires, temperature probes, things like that. It's an immensely complicated job. But fortunately, to describe our gravity experiment, we only need to consider 3 of those magnets. I'm going to call the top mirror, which is this mirror coil over here, the bottom mirror, which is this coil over here, and the optical magnet, which is running between them. The remainder of all these magnets, and there are about 30 of them, are used to prepare the plasmas properly, but not further used, or they're intended for future higher precision measurements. And what we do is we take this basic trap with only these 3 magnets left in it, And that forms a potential well, particularly in the axial direction. So this mirror makes a bump in the field here. The bottom mirror makes a bump in the bottom. There's a minimum in the center. So if we place a particle into that trap, it's just going to bounce back and forth between the top and bottom mirrors. The only function of the octopole magnet, by the way, is to keep the antihydrogen atom from going out in the transverse direction. And we can kind of ignore its presence, though it turns out that the actual orbit dynamics here is immensely complicated. And that matters, especially for higher precision experiments. That was first understood, actually, by my undergraduate student. And really was remarkable for Adrienne to be able to figure this all out as an undergraduate student. In our meetings, we seem to talk about his effects, her effects almost every day. In any case, we actually put multiple antihydrogen atoms inside of the trap. And obviously, they don't all have the same energy. Some of them have very little energy. Some of them have much more energy. The more energetic ones get closer to the top and bottom mirrors. It's not, by the way, a harmonic oscillation, because this is not a harmonic trap. But in any case, we can then start to play with the strength of these mirror coils. In particular, what we can do is we can lower the magnetic field on that's produced by these mirror coils. And what that's going to mean is if we continually lower that magnetic field, what's going to happen is that the orbital extent of the particles is going to get longer and longer. They're going to go into and eventually almost stop in one of the mirror coils if the mirror coils are weak enough. When they stop in that mirror coil or come to almost a halt, they're moving so slowly and have so little kinetic energy left over that finally the very, very weak gravitational potential can start to affect their motion. What we've essentially created is a magnetic balance. You know how you can make a balance? You can have two pans and you can detect 1 gram on top of many kilograms. Well, we're doing exactly the same thing by making a magnetic balance. And then gravity can tip the balance over to one direction or another. So for instance, if gravity points normally, we know that the actual potential is going to be slightly lower at the bottom when the magnetic potential is precisely balanced, and the actual potential is going to be slightly higher at the top, which means that a particle is more likely to fall out the bottom of our trap because it can escape over the wall at the bottom sooner than it's going to be able to escape at the top. And that's precisely what it does do. Eventually it gets to the point where it escapes, and when it escapes, it's going to annihilate on the wall, and we can count that annihilation. That leaves it leaves some remaining antihydrogen atoms left in the trap, of course, but we're actually continually lowering the magnetic field. So eventually a slightly less energetic particle will reach the point where it's going to stop in the trap and it will escape. All of the particles inside of the trap will eventually escape if we bring those mirror coils down to a zero field. But some of them will escape upwards. If it turned out that the gravity was pointing upwards, the barrier at the top would be weaker than the barrier at the bottom, and they would escape upwards. And here's a cartoon of all of this. It's a cartoon, not a simulation, which was developed by the National Science Foundation. You can see that we start out with a bunch of antihydrogen atoms trapped in the middle of our mirrors. And then as the mirror fields are reduced, what happens is their orbit extent increases and they start to fall out. Most of them fall out the bottom, but it's a little bit of a statistical effect, and some of them fall out the top. We can count the numbers that fall out the top and the bottom, and we discover that most of them, or in this cartoon anyway, most of them fall out the bottom. So what actually happens in the experiment? When we design the experiment so that the mirror coils are precisely balanced, we found experimentally that 95 atoms fell downwards, and 37 of them fell upwards. So not only 72% of them fell downwards. And you might wonder why 100% didn't fall downwards. There are a couple of reasons for this. One is that the mirrored ramp down rate is not entirely adiabatic, so some of them just arrive in the wrong place at an unfortunate time. But a more important reason that it's not precisely all up or precisely all down is that the magnetic balance is only precisely balanced at the central axis of the trap. As you move off the axis, the balance shifts a little bit, and that leads to particles being annihilated in different regions. There are also, of course, statistical and systematic errors. We've simulated this process very precisely, well, as precisely as we can, and the simulations predict that under these conditions where they're balanced, 83% of them should have fallen downwards, which unfortunately isn't 72%, but it's not so far from 72%. So we're beginning to have an experiment, but I wouldn't call this an experiment so far because there are no knobs, there's nothing we can turn. Fortunately, there is a knob that we can use inside of these experiments, and that's to deliberately unbalance the trap by changing what we call the magnetic bias. In other words, instead of trying to make the magnetic fields exactly and precisely the same on both sides of the trap, what we can do is, for instance, deliberately increase the magnetic field on the top mirror. And that's going to mean the fields are stronger there, so that's going to force particles to be more likely to fall out the bottom of the trap. This is actually what we call a positive bias. When the top mirror is too strong, stuff should fall downwards, preferentially. But we can also make a negative balance, where the bottom mirror is stronger than the top mirror, in which case stuff should fall out the top of the trap. And the natural unit here is to think about g, the acceleration of gravity, and 1g corresponds to a field of 4.5 Gauss. So what do I mean by that? If you figure out what the gravitational potential difference is between the top mirror and the bottom mirror, and then calculate the magnetic field that will make a different magnetic potential difference, which is precisely equal to that gravitational potential difference, the amount of change in the magnetic field that you need is precisely 4.5 Gauss. But that's not the only thing we can do. We can make what we call an equilibrium balance. If you make the bottom of the trap slightly stronger than the top of the graph, a bias of -1g, 4.5g stronger, then the mirror fields, the magnetic mirror fields, and the gravitational fields should cancel out exactly. And you should get just as many particles going up as you got going down when they escape. And we can change this bias and have all sorts of different biases. Here's a summary of some of our data. It's a slightly complicated graph, but these are the particles that fall out in the down direction. Here are the particles that fall out in the up direction. Each individual graph is for one value of the bias. And you can see that when we have a strong positive bias, almost everything falls downwards. A strong negative bias, almost everything falls upwards. If we have no bias, this curve over here, you can get that 73% ratio that I was referring to earlier. And also, if you go to what I call the equilibrium balance, where the magnetic fields and the gravitational fields exactly cancel, you should get just as many falling downwards as upwards, and that's this case over here. Now, it's a little bit hard to be quantitative here, so let's put that all in a graph. These points are our data points with statistical and some systematic errors included. And you can see that almost everything falls downwards. Just to repeat, when the bias is negative, everything falls upwards when the bias is negative, when we have a strong magnet on the stronger bottom than top mirror. Everything falls upward. Everything falls downwards. Downwards, yes, I can read some of the time. When our top mirror is stronger, which is the positive bias. You can also see our simulation curve with some error bars from what we think are the simulation data here. And you can also see that the fit is not bad, but it's by no means a perfect fit. So what do? Well, it turns out that we can simulate any outside bias. It doesn't have to be what we observe in nature for normal matter. We can simulate repulsive gravity, where particles would fall upwards at the rate at which normal matter falls downwards, and you get this purple curve, which is not even close to our data. So we've strongly ruled out the idea that antimatter falls upwards. We can also simulate no gravity. In other words, antimatter shouldn't be affected by gravity at all. That's this green curve. It's closer, but it's pretty clear that our actual data fits normal gravity better than it fits the no gravity simulation. And we can keep on simulating different amounts of gravity, and the net result, here are some of those curves, the net result is that we were able to measure that the acceleration of gravity is equal to 3/4 of the normal acceleration of gravity. Now, please don't go away from this talk saying that I think that gravity, antimatter falls a little bit more slowly than normal gravity. I'm sure that well, we'll come to what sure means in a second, but I'm sure that this discrepancy with 1 comes from our systematic and simulational errors. And it'll eventually, as we get better at doing this, it will become equal to 1, which leads to a philosophy discussion, which I'm not going to have here, but it's about confirmation bias, which is really a problem with experiments like this. I'm sure some of you are familiar with this problem in other contexts, but it's a really difficult problem. In any case, I'm going to conclude with just discussing some of the technical details of how to make this experiment run. One of the things that we obviously need is very, very precise magnetic field control. Our mirror coils go up to about 1 Tesla, but we need to be able to control the fields to significantly better than 4.5 Gauss. In fact, our design goal is to control the fields to about a 100th of a percent. And that means controlling the currents in the supplies to 100th of a percent. Now that is feasible with commercial power supplies under normal circumstances, but we don't have normal circumstances. We're ramping the magnets down in about 20 seconds. And commercial power supplies will not track and can't be controlled to 100th of a percent on that sort of time scale. So we've added an external control loop. What we do is we measure the current very, very precisely using a DCCT, and we feed back on that with an FPGA to control the current that we order from our power supply. And so we send that current through both the bottom and the top mirrors. So identical current through both of those mirrors, which is just the zero bias condition, but it's established very, very precisely. But we don't need just zero bias. We actually need to be able to make these currents slightly different. So what we do is we use what we call a tickle supply. The main supply goes 70 amps. The tickle supply goes only plus or minus 1 amp. And that just goes through the top mirror. So that's how we create our different biases. So it sounds like we're done. We've got ample control of the current. We're not even close to being done. Because the problem is that you can't actually make mirror coils which are accurate to 100th of a percent. It's just technologically impossible to wind the coils so they're even any place close to 100th of a percent in being identical. And we're very careful about this. Here's the top mirror, bottom mirror being wound. Here's the top mirror. And at every layer, we take a photograph of where the wires are. And on the next layer, we adjust that layer to compensate for some of the errors that we might have observed. But it's still impossible. So what do we have to do? We actually need to be able to measure the magnetic field that's being produced by these coils very, very precisely. Easy enough. NMR, you say that should work, except that it doesn't work at all, because NMR samples freeze out typically when you're down at liquid helium temperatures. And you won't be able to get any signal at all. Besides, NMR samples tend to be relatively big, and we need a very, very tiny localized measurement of the magnetic field. So, all right, Hall effect sensors, they don't work either, because it turns out that every time you cycle a Hall effect sensor down to liquid helium temperatures and back up, they change a little bit. So they're not going to work. So we had to come up with something else, a new technique. And we did, it's something that we call electron cyclotron resonance, or ECR. That's a term of art in plasma physics, ECR, magnetometry. And here's how it works. What we do is we take a target plasma and we move it to where we want to measure the magnetic field. And then we send in microwaves. When the microwave frequency hits the cyclotron frequency, there's going to be a resonance and the plasma is going to heat up. We can measure that heat increase. And by scanning, we can just simply determine what the magnetic field is. And this sounds simple enough, but unfortunately it's not at all simple, because it turns out, due to plasma physics effects, there are multiple peaks when you do this process. You get one peak, which is the peak that you want, this peak over here, but you also get side bands. And the side bands are a function of the bounce frequency of the electrons in the plasma. So what do I mean by that? Well, here's our plasma, and the electrons are bouncing back and forth at some frequency. If the plasma trap is shallow, that's a slow frequency. If the plasma trap is strong, the plasma shortens and the frequency goes up. And this is a scan as you go away from that point. So each of these high side bands are when the bounce frequency is very high. What we obviously want is the stationary frequency, which doesn't depend on the bounce frequency. And we can measure that actually exquisitely well for a plasma, exquisitely well, but there's an additional complication, which is that if you take a look at the fine details of that central peak, in other words, here's a fine scale scan of the frequencies, it turns out that that splits up too. And so there are additional side bands. And what's even worse is that the side band that you want, the one that doesn't move, is not even the biggest side band. These side bands, by the way, come about from the fact that the plasma is rotating, and they come from the rotational frequency of the plasma. Nonetheless, if you can identify this stationary side band, we can make measurements to about 1 part per million, which is almost unheard of, by the way, in a plasma physics experiment. And that's more than good enough for our experiment. So you think you're done. And you kind of are done, because you can make magnetic field maps. You can move your target plasma to different places in the plasma and do the cyclotron heat resonance magnetometry there. And you can get maps of what the magnetic field are. And here are some representative maps where we deliberately wanted the bottom field to be 4.5 Gauss stronger than the top field. And we get that. The only trouble is, there are two more problems. There are two more problems. One has to do, again, with some basic freshman physics. You all know that you can make a solenoid, and when you run current through the solenoid, you get a magnetic field, right? Everybody knows that from freshman physics. And if you open the switch and there's no more current running through your solenoid, the magnetic field goes away. What could be simpler? It's not at all simple in a superconducting magnet, because it turns out when you have a superconducting magnet, when the current goes to zero, there's still a remnant, what's called persistent field, which can be quite large. For instance, in our magnets, when we go from 70 amps, which is 1 Tesla, down to 0 amps, which should be 0 Gauss, we get a field of about 20 Gauss. This is universally true in superconducting magnets. And the reason for this has to do with the way magnet wire is constructed. Here's a superconducting magnet wire. Well, you can see it's actually complicated. It consists of a copper matrix and superconducting wires, which you probably can't discern unless you're close to the front, are embedded in the copper matrix. In our case, for reasons that are a little complicated, we use a lot of filaments of this superconducting filaments, which are embedded in the copper matrix. We use 678 of them. But if you consider one individual filament, it has a very small diameter, about 9 microns. But you can develop current loops inside that filament. And those loops are going to be persistent. While they do have a very, very tiny inductance because the diameter of the loop is going to be very, very small, they also have essentially zero resistance. So the time constant can be anything you want out of these systems. In practice, it ranges from seconds to hours. Here's a graph of some measurements. And there are only two things that save us from this being a disastrous problem. One is that the top mirror and the bottom mirror have essentially the same decay curve. And the other thing that saves us is that if you repeat the same current history over and over and over again, you get exactly the same curve for the decay of these persistent currents. So if we're very careful to just make every measurement repeatable, we can make our measurement. And then finally, the thing that, the last problem is that it takes tens of seconds to measure the field with ECR. And we're ramping down our magnets in 20 seconds. We want to make measurements while we're ramping down. And so we needed to develop a new technique. We call it, well, Andrew Christensen, who invented this, one of my graduate students, came up with an impossible to say name called magnetrometry, because there's something called the magnetron effect. But I'm only going to outline it with a picture. A former student, Eric Hunter, developed what we call a plasma reservoir technique. We can put a lot of particles into some place in our machine, and then we can gradually pop off tiny target plasmas from the reservoir. We can make essentially identical plasmas. Out of every reservoir, we can quickly make something like 200 plasmas that come off. We can move those plasmas to the place where we want to measure the field, and then we can park it there, lower the confining field. Because of the patch effects that I mentioned before, that moves the plasma off axis. We can snap the electric field back onto the axis, snap the electric fields back to stronger values. And we can observe this magnetron motion, this circular motion that I saw a moment ago. That's inversely proportional to the magnetic field. And so we can make a measurement by just measuring how many times the plasma goes around and around. And that works. Here's some data. Here's the green curve is what we wanted. The green dots are what we got. There are some gaps in the records for complicated reasons. And it looks like a great match, but it's actually off by a couple of Gauss. But we can compensate for that by changing the bias current in the Tickle supply. Anyway, that's all I'm going to say about the experiment. In conclusion, I'd like to say that the chance that we're ever going to observe something interesting is very, very small, negligibly small, perhaps. But the reward for measuring something interesting is simply enormous. And whether or not you like this type of experiment, these are called null experiments in general in physics, it's a matter of taste and style. In the beginning of my career, I would have said I hated this. But in fact, this has been an enormously fun experiment to do. And the reason why people have different opinions about this is that you can calculate the expected value of this sort of research. And that's going to be equal to 0 times infinity, which is whatever you want it to be. So for some people, that's going to be high. For many people, it's going to be low. But it's been a lot of fun. And we've done a lot of measurements on antihydrogen. Very briefly, we've been able to measure this microwave spin flip measurements. We did a crude measurement of gravity. We bounded the charge of antihydrogen to about 1 part per billion. We've measured the 1s, 2s frequency to about 2 parts per trillion, which is approaching the levels that are attained by measuring the 1s, 2s in normal hydrogen. We're not there yet, and they're scared, and they've started to do better. They've started up their experiment to this is the Ted Hensch group, to improve their measurement so that they stay ahead. In any case, we've measured the hyperfine structure. We've measured Lyman alpha line, which we can now use for laser cooling. And most recently, we were able to measure that gravity, unfortunately, pulls antihydrogen atoms downwards. So this is a big effort. Here's a picture of the team, of part of the team 1 year. I'm just going to put up all the people from Berkeley that have been involved, who are, well, many of the people from Berkeley who've been involved. You can see there are actually a lot of undergraduates who spent time at CERN, and they've been a great help. Thank you very much. I hope you learned something interesting.
Questions for Joe?
So, of course, this is really nice in many ways, technically, and this is great. On the other hand, I would have thought the best way to do all those cross-checks is to take the entire thing, turn it upside down, and check that it matches up. Now, I know it's hard, but I'm wondering how to do it. It's kind of an obvious, right?
Yes, it would be great if we could do that, but we can't do that. This is an incredibly difficult experiment. We're never going to be able to, I mean, we'd have to rotate the CERN ring, for instance, the decelerator ring, because they're a straight...
Well, you're injecting the thing from the bottom.
Yeah.
Can't you just, sorry, just is the wrong word, but, you know, there's a gate valve, you turn it around.
Okay, so there is an experiment at CERN which is planning to take antiprotons from our facility, our building, put them into a dewar, valve off that gate valve that you suggest, take a 3 Tesla, 5-ton magnet, pick it up on the crane, and move it to another facility. And I can say only one thing about that experiment. I do not plan to be in the hall when they move that magnet. It's not really so easy. The proper way to do the comparison measurement, sorry to be so judgmental, but I'm going to say the proper way, is to put hydrogen into the machine. And the problem with putting hydrogen into the machine is that we can't detect hydrogen the same ways that we detect antihydrogen. It's very hard to work with antimatter, but once you get it, it's easy to see that you have it. The efficiency of our detector is about 68%. So we can see that we have it. We haven't yet figured out exactly how to measure. Though actually, one of the younger people on the experiment has made great progress on this, but we haven't exactly figured out how to measure the hydrogen that would come in these experiments. It's certainly one of our goals, is where we want to be. And you're absolutely correct that we need a better way to do this, especially as we move towards higher precision experiments in both the spectroscopy and the gravity experiments. It's going to be easier to use hydrogen in the spectroscopy than it's going to be in gravity, but we'll get there eventually, we hope.
Good questions.
Yeah, just in your error bars, you had this simulation error that was comparable to the statistical and schematic uncertainty. What goes into that? I was kind of surprised.
A lack of knowledge of the precise magnetic fields, particularly off-axis, is the primary thing. I mean, to be honest, we also have a discrepancy between the simulation having to do with the rate at which parallel and perpendicular energy mix, which we have not been able to determine the reason for this. It seems like it should be a simple problem to get the simulation exact, and yet it turns out not to be.
I seem to recall in the late 80s, there was a Lear, an experiment called Obelix. Ugo Gastaldi and others, they decelerated antiprotons out of Lear and shot them over the parking lot on the east wall, and measured, or tried at least to measure the deviations between antiprotons and protons, because they the proton beam and antiproton beam.
I'm not particularly familiar with that experiment. There was yeah, I'm just not familiar with that experiment. It's not part of the...
Yeah, maybe they failed. Maybe they didn't.
All I can say is it's not part... I only joined this field in 2004. I designed this experiment in 2012. Well, I started to design it. It was a long process. It's not part of the lore of the field. Now, it's possible that people have just totally forgotten something. It's certainly true that Lear exists, and antihydrogen atoms were made there at Lear.
Yeah, because back then they had a lot of antiprotons.
Yes, they had a lot of antiprotons.
Gabriel and Castaldi.
That's right. There was a lot of good stuff was done early on there, but I'm not familiar with any gravity
They
experiment.
probably failed. It's much more precise.
Well, the Fairbank failure is much more interesting.
Yeah, negative outcome is good.
Yeah.
Yeah. A lot of the technologies you described are very reminiscent of the guys from MIT who were trying to do Bose-Einstein condensation on hydrogen, on spin polarized hydrogen. Eventually, when they managed, they did some laser cooling. They also did some RF type of cooling at the end, and all kind of things like this. Are there any other ideas you have for further cooling this stuff and further?
Well, the laser cooling works reasonably well down to about 20 millikelvin. On top of that, we actually have a paper we've been writing for about 5 or 6 years, but it's just about to be submitted. I'm sure many of the older people here have those papers that just somehow never seem to get done. But we're arguing at the moment whether anti-atom has a dash between the anti and the atom, or it's just one word. So you can tell we're really close to being finished. And that involves adiabatic expansion cooling of the antihydrogen atoms. Those are the only two things that we have on our plate. We don't have good access, and it's a cryogenic, because it's a cryogenic trap, and the nearest access is about 1 meter away. So other techniques are hard to deploy on a short-term basis, but we obviously would like to be able to cool them further than that we've achieved so far. We have spectra that have been made with the cooled antihydrogen atoms. Cooling them would also really help with gravity as well. And so all of this, the spectra should be coming out soonish. Gravity is a year or two away, but that's where we're headed.
I just wanted to point out that with us today is Dr. Fred Witteborn.
Oh.
Bill Fairbank is the pioneer of antimatter gravitational experiments here.
Okay, I'm honored to meet you.
Well, I'm honored to meet you because you've actually succeeded. I wondered, what is your best reference to this result? I mean, if I wanted to...
I'm sorry, it's actually... it's this paper over here, the last paper here, which you probably can't too easily read, so I'll just call it out. It's Nature, volume 621, page 716, published in 2023.
Also, we prefer you refer to it as the challenged Fairbank experiment rather than the failed.
Well, the gentleman who's talking was the graduate student at the time. So.
Are there any further questions? All right, if not, thanks for again.
Thank you.
Thank you, that was lovely. That's really cool.